Welcome to The Explainer. Today, we're taking the invisible, microscopic world of organic chemistry and turning it into a clear, rule-based story. You know, if you've ever looked at a complex chemical equation and wondered how on earth a jumble of letters and lines actually translates into real-world transformations, well, you're in exactly the right place.
So let's dive right in by recognizing that understanding how these molecules interact is so incredibly powerful, it literally wins Nobel Prizes. Back in 1950, Otto Diels and Kurt Alder won the award for describing a highly specific reaction mechanism between a conjugated diene and a substituted alkene. It was a total game changer, becoming a foundational tool in synthetic organic chemistry. But to really appreciate masterworks like the Diels-Alder reaction, we first need to decode the basic language of how chemical bonds break, move, and form.
We're going to build our knowledge sequentially today across 5 key areas: the mechanics of reactions, breaking bonds, also known as fission, nucleophiles and electrophiles, electron displacement effects, and finally, classifying organic reactions.
All right, Section 1, the mechanics of reactions. Let's start with what an organic reaction actually is and how we track it.
The crucial thing to remember here is that a reaction is definitely not magic. It's a very specific, step-by-step pathway where a substrate, that's our starting organic molecule, is transformed into a product by a reagent. And every single step in this pathway has to push through an energy barrier. This often creates these really short-lived intermediates or transition states before finally settling into the final product. And here's a pretty fascinating rule of thumb. Think of it like a traffic jam on a highway. The absolute slowest step in this entire sequence dictates the overall rate of your entire chemical reaction.
And this whole process relies on an intricate, microscopic dance of electrons. They always follow one of 3 specific movements. In organic chemistry, we actually track this flow of electrons using curved arrows. An arrow just starts where the electrons are and points to where they're going. So, whether a lone pair shifts to form a new bond, a bonding pair retreats back into a lone pair, or a bond entirely relocates, literally all organic reactions are just variations of these 3 fundamental choreography steps.
Moving to Section 2, breaking bonds, or fission. Because before we can build anything new in our chemical story, the old bonds absolutely have to be broken.
Covalent bonds can split in 2 fundamentally contrasting ways, equally or unequally. In homolytic cleavage, the bond breaks symmetrically. Imagine 2 atoms sharing a pair of electrons. They just split the pair right down the middle. Each walks away with a single unpaired electron, forming what we call a free radical. In heterolytic cleavage, however, the bond breaks unsymmetrically. Basically, the more electronegative atom bullies the other one, taking the entire pair of bonding electrons for itself, which results in a negative anion and a positive cation.
To ground this in the real world for a second, homolytic cleavage creates free radicals. These are basically the highly reactive villains in the human body. Because they have that one unpaired electron, they are desperate to find a match, making them incredibly unstable. When our bodies are exposed to things like X-rays, cigarette smoke, or heavy air pollution, these free radicals are generated. They aggressively disrupt cell membranes and can even increase the risk of cancers and heart disease. But the heroes of this story? The antioxidants found in our fruits and vegetables. They readily neutralize these radicals before they can cause cellular chaos.
All right, Section 3, nucleophiles and electrophiles. Once those bonds break heterolytically, we're left with a cast of characters desperately looking for new partners. Let's meet them.
Think of nucleophiles as the wealthy benefactors of the microscopic world. I mean, the name literally translates to nucleus-loving. They have extra electrons to share, often carrying a negative charge like a chloride ion, or possessing unshared lone pairs like an ammonia molecule. Because they are so electron-rich, they're constantly on the prowl for an electropositive center where they can donate those electrons to form a nice, stable, covalent bond.
On the flip side, we have electrophiles. These are our electron-deficient characters. Meaning electron-loving, they are constantly on the hunt for a negative charge to stabilize themselves. These can be positively charged ions like carbocations, or neutral molecules that simply have room to accept more electrons, like carbon dioxide or Lewis acids such as aluminum chloride. So if nucleophiles are the generous donors, electrophiles are the enthusiastic recipients.
Section 4, electron displacement effects. Now we get to look at the unseen forces, the invisible poles that dictate exactly where these nucleophiles and electrophiles will actually attack.
There are 4 main displacement effects that shift electron density either permanently or temporarily. Think of these effects as the underlying gravity of the molecule.
We have the inductive effect, which polarizes sigma bonds, the temporary electromeric effect, which shifts pi electrons when a reagent approaches, resonance, which stabilizes molecules through delocalized pi electrons, and finally, hyperconjugation, which does something similar but uses sigma bonds instead.
Let's focus on the inductive effect for a minute. It basically acts like a microscopic tug of war, profoundly altering a molecule's reactivity and acidity based entirely on who is pulling the electrons. And it's a permanent phenomenon. Highly electronegative atoms like fluorine or chlorine act as -I groups. They selfishly pull the shared pair of electrons through the covalent sigma bond toward themselves. On the other hand, +I groups like methyl or ethyl generously push electron density away. This is exactly why chloroacetic acid is a much stronger acid than standard acetic acid. That chlorine atom acts as a -I group, pulling electrons away and making it incredibly easy for the molecule to just give up a hydrogen proton.
Now contrast resonance with hyperconjugation. While resonance deals with the sharing of pi electrons, like that perfectly distributed electron cloud you see in a benzene ring, to stabilize structures, hyperconjugation is a totally unique effect. It cleverly uses sigma bonds to achieve a similar stabilizing result. In hyperconjugation, the electrons from a single sigma bond, say a carbon-hydrogen bond, overlap with an adjacent empty p orbital. Because it involves the apparent breaking of a single bond to supply electrons for this delocalization, chemists playfully call it no-bond resonance. It is the exact reason why a tertiary carbocation is vastly more stable than a primary one.
And finally, Section 5. Classifying organic reactions. Let's zoom all the way out for our grand finale and see how all these micro-interactions result in the main macro classifications of organic reactions.
Despite the literally dizzying variety of organic molecules out there in the universe, almost every complex organic reaction you will ever encounter fits neatly into one of these overarching categories. By identifying which category we're looking at, we instantly know the plot of the chemical story being told. Let's look a bit closer at a few of them.
Notice the really clear distinction here? Substitution is a direct swap. One atom or group leaves, and a new one takes its exact place, kind of like a chemical game of musical chairs. Addition, however, is entirely different. It forces two completely separate molecules to merge into one single product. This is the absolute hallmark reaction of unsaturated compounds. Those are the ones with double or triple bonds. When they undergo addition, one of those multiple bonds breaks to grab onto the new incoming atoms, fundamentally changing the hybridization of the carbon atoms from, say, sp2 to sp3.
Then we have elimination, which is essentially the exact reverse of addition. Instead of breaking a double bond to add things on, we're stripping atoms away from adjacent carbons to create a brand new double bond. For instance, if you take N-propyl bromide and react it with alcoholic potassium hydroxide, you eliminate a hydrogen and a bromine atom, leaving you with propene. The molecule just trims down and forms a tighter unsaturated bond.
Now, speaking of these reaction categories playing out in everyday life, let's talk about oxidation. Ever wonder why apples turn brown? That enzymatic browning on your apple slice is a macro result of these exact microscopic chemical processes. When you cut an apple, you expose its inner cells to atmospheric oxygen. An enzyme inside the apple called polyphenol oxidase immediately gets to work oxidizing the phenolic compounds present in the flesh, turning it that familiar, slightly unappetizing brown color. Ultimately, oxidation and reduction reactions are simply two sides of the exact same coin. They track the flow of oxygen and hydrogen atoms. Most oxidation reactions of organic compounds involve either grabbing onto oxygen or letting go of hydrogen. Reduction is the exact inverse, pulling in hydrogen or shedding oxygen. You literally can't have one without the other in a chemical system. They are perfectly balanced ledgers of atomic exchange.
So it all begs the question, if we can master the manipulation of these specific bond fissions and electron flows, what entirely new, life-saving medicines could we synthesize next? By understanding the fundamental rules of how molecules break apart, how their electrons push and pull, and how they ultimately reassemble into predictable categories, we aren't just memorizing textbook formulas. We are unlocking the ultimate toolkit for building the future of chemistry. From neutralizing free radicals in the body to synthesizing the next generation of therapeutics, it all starts right here with the dance of the electrons. What will we build next? Keep exploring, keep questioning, and I'll catch you in the next explainer.